So 22. Right? You just, it wants the rate constant, that's K, for each of these experiments. So you're going to have to, like, you'll take that first line, that first experiment, plug that data in here in this equation, solve for K, and then do that 4 more times with the other data. So you'll end up with 5 calculations of K. And then finally, you just take the average, add up all those K's and divide by 5. You should have an average K .9 times 10 to the minus third liters per mole second should be your average when you get it. K average. You have to get all of them to be able to obtain this.
Oh, sorry.
Okay, any other questions about the homework?
Can you do 23?
23? 23. Okay. We are working on 23 now. The decomposition of nitrosyl chloride was studied. Hey, do y'all see where it says the following data were obtained where? See that rate equals negative change in NaCl concentration over time, delta T? Remember on the first day, I told you guys, that is just going to be a symbol. You're not going to have to do anything with that. It's just part of the reading. It's just part of the language. Okay, so on part A, what is the rate law? We got to find out the rate law. All right, so we have rate equals K. Okay, finding out the rate law means we have to find this exponent n is what we got to do, right? We got to find this exponent n. There's only one reactant. That's no different from having 3 reactants. When you have 1 reactant, you should be jumping up and down inside going, I only got to do this once instead of 3 times. Okay? All right, so we don't have to worry about keeping anything else constant. We only have 1 reactant. So just pick 2 experiments. Kelsey, give me 2 experiments. Second and fourth. Okay, I'm going to put the 4th on top of the ratio because it's bigger. All right, so 4 times 10 to the 16th. This is experiment 4 over experiment 2. I write that down to remind myself of which lines I'm looking at because I will forget. I get so engrossed in this that I'm like, what am I doing? It's just to keep my thoughts straight. You don't necessarily have to write it down. All right, so we got rate 1.06 times 10 to the 5th. Molecules per cubic centimeter second. Equals K. I'm just going to write all of this first experiment and then I'll go to the denominator. All right, NaCl 4 times 10 to the 16th. Okay, so that's all of experiment 4. Thank you, Dustin. Okay, experiment 2, the rate is in the right-hand column. You'll see that of the table. 2.66 times 10 to the 4th. I look at the top of the column and it tells me the unit, molecules per cubic centimeter second. Not really important for part A, but you need to get in the habit because on part B, you've got to get the rate constant K, and it has to have a unit, and it's always different. And I should have put that in parentheses instead of square brackets. Okay. 2 times 10 to the 16th. Nothing, well, K is the only thing that cancels here. Bless you. Again. 3.98 unit to cancel. That should be 2, right?
Well, it's right now, we're used to 1.06 times 10 to the 5th divided by 2.66 times 10 to the 4th.
Yes. Equals 3.985. And 4 times 10 to the 16th divided by 2 times 10 to the 16th equals 2 to the nth order. Now, you can punch this on your calculator, but 3.985, is that close enough that we can round that to 4? Sure. Now, if it were 3.5, no, we couldn't. But yeah, this is fine. So let's round that to 4 equals 2 to the nth order. So now we say to ourselves, Sadie, 2 raised to what power equals 4? 2. So that means n equals 2. Reaction is second order. With respect to NaCl concentration. But they want the rate law. They want the rate law. So to get the rate law, you need to take right here, this N, erase it, and put in a 2. This is the rate law. When they say, what is the rate law, they want what's in the red box here. This is method of initial rates. This is expressing the rate law so that it's showing how reaction rate, speed, is a function of concentration. Because look at it, in the rate law, you've got rate, you've got concentration. Nowhere in here do we have time. Time is going to be in the integrated rate law. Okay, the part B wants to know the rate constant. So we're going to take our rate law, we're going to pick an experiment, plug in the values, and solve for K. All right. Taylor, pick an experiment. 3. Okay, we'll use the third experiment. If you use something different, you should see that you should come out with the same K. 1 times 10, let's see, rate is 6.64 times 10 to the third. Once again, this is where the units are important. Okay, concentration 1 times 10 to the 16. Now we solve for K. Is that what we have for the number? Yeah, check me on the number. Okay, let's come over to the side and determine the unit. We have a molecule per cubic centimeter second divided by molecule squared per cubic centimeter squared. Okay, so that becomes molecule per cubic centimeter second times cubic centimeter squared over molecule squared. What cancels? One molecule, 1 cubic centimeter, and that's it, right? So our unit is going to be cubic centimeter molecule second, right? Okay. Did y'all get this number? Okay. Cubic centimeter per molecule second. Any questions? You betcha. I like to see. Calculate the rate constant for the concentrations given in moles per liter. Okay, what's our rate constant? Right? This is our rate constant, K. It's just, all this is a factor label on part C. It's just dimensional analysis. It's just, it's just converting the same quantity into different units. You know, like if we have, man, I left my change at the house. I was going to say, we have 4 quarters, right? Well, how would we express that in dollars? $1. It's the same quantity, you know, it's the same value, it's just expressed in a different unit. Well, that's what we're doing here. That's what we're doing here. Okay, so .64 times 10 to the negative 29. Now, look at that unit. Cubic centimeters is upstairs. Molecules, seconds are downstairs. So I'm going to put it in a factor label like that. Okay. We've got to get cubic centimeter changed to liter. Okay, 1 cubic centimeter is the same amount of space as 1 milliliter. So 1 cubic centimeter is 1 milliliter. All right, that unit's gone. How many milliliters in a liter? Milliliter. 1,000 milliliters in 1 liter. That unit's gone. Okay, we got liters now. Okay, and how are we going to change? Now we got to get rid of molecules and change it to moles. Is everybody good with what we've done here so far? Okay. All right. What is the relationship between molecules and moles? If we had this many number of marbles, it would cover the Earth in a depth of what, 2 miles? 6.022 times 10, 23rd molecules is 1 mole. Yay! Ain't it cool? All right, so molecules is downstairs. So we're going to put it up here to get rid of it. And change it to mole. I know that looks weird, but is it not logical? Okay. So we put these numbers where they belong. Mole gets a 1. Avogadro goes here. Now, if we were to stop here and crunch numbers, we have what? We would have liters over mole second. Is that what they want? Yeah, it says calculate the rate constant. So we're doing rate constant, right? Rate constant is in terms of concentration over time. So you have to keep the time in there. But they're saying, when they say 4 concentrations given in moles per liter, they're saying, what if they give us data in moles per liter? What kind of rate constant will we get? It would involve moles per liter in seconds, because your rate constant has to involve time. So your times, because see, look right here. Look at this concentration. This concentration was molecules in cubic centimeters, right? But the rate constant always has time in it. If you need to, write yourself a note. Rate constant, K, will always have a time unit. Don't let the question throw you. Rate constant, K, will always include a time unit. It may not always include a concentration unit, but it will always include a time unit. So we punch this in. Okay, did y'all get 3.9986 times 10 to the minus 8? Check me, y'all know how I am. We'll back later. Not if we keep turning it up. How Sarah, you come through? Can you survive? Okay, y'all check on that, please. Right, okay. We need 3 sig-figs. How are we gonna round that to 3 sig-figs? Okay, so K equals 4.00, don't forget this. Times 10 to the minus 8. And what's our unit again? Liter per mole second. That. Yay! Neato.
But it says moles per liter though.
Like I just got that saying. Look at the whole sentence again. What, are you talking about in the book?
Yeah.
Yeah, look at it again. Calculate the rate constant for the concentrations given in moles per liter. They're saying, okay, if you've got concentrations given in moles per liter, what would be your rate constant?
Okay.
Rate constant will always include a time unit.
Okay.
Yeah, it may not always include a concentration unit. You'll see that with integrated rate law, but it will always have a time unit. Anything else? Okay, so after this past couple of days, right now, how are you feeling about method of initial rates? Do you feel like with just a little bit more practice, you can master it? Okay, I think so too.
Will you do 24?
Sure.
I'll comprehend question.
Yeah. Okay, so let's look at 24. The following data were obtained for the gas-phase decomposition of dinitrogen pentoxide. We learned how to name and write formulas for that last year, didn't we? The easy days gone by. You didn't think they were so easy back then, though, did you? You're growing intellectually. You are growing. Your brains are getting stronger. No pain, no gain, right, Sarah? All right, so we've got our data. Defining the rate as change in N2O5 concentration over time. Write the rate law and calculate the value of the rate constant. Okay, here we go. So our rate constant is going to, or our rate law, excuse me, is going to look like rate equals K into O5.
Where's the little zero outside of it?
Huh?
Like right outside the.
Oh, that is, that means time equals 0 seconds. Do y'all see what Kelsey's talking about? And once again, I've been doing this for so long that I tend to take stuff for granted. So please, if you are questioning something, speak up. No question is dumb, I promise you. Okay, some of the answers I give you might be, your questions are not. Right here, this means at time equals 0, right? Your future professors might call this naught. You've heard of double naught sky? Have you not? Do y'all not watch Beverly Hills? I'm just missing out on a lot. Watch it. Jethro's going to be a double naught spy. Anyway, Kelsey, what that means is initial concentration. That simply means initial concentration, which is the concentration at T equals 0 seconds. Okay. All right, so this is the form of our rate law. We need to find out what our reactant order N is. Remember, N is reactant order. That's what we've got to find in this first part. So we, once again, only have one reactant. Yay, we only have to do method of initial rates one time. So we're going to pick 2 experiments. Andy, would you, oh, you're busy punching. I'm sorry. I'll get somebody. Aaron, pick up 2 experiments. 2 and 3. Right, we're going to use 2 and 3. All right, 3 is bigger. Okay, so rate for 3, 3.26 times 10 to the negative third moles per liter second equals K. Concentration 0.275 moles per liter in order. Experiment 2, 2.26 times 10 to the negative third moles per liter second equals K. 0.190 moles per liter to the fifth order. All we did here was take 2 experiments, put their data into the rate law form, make it a ratio of 2 experiments. Now we're going to solve for the exponent, the reactant order. K cancels, units cancel. Okay, right here, this ratio is what? This right here is 1.44 times 10 to the minus third. Is that right?
I just got 1.44.
Okay, let me check it again. I'm gonna hit it wrong. It should, because those, when you divide exponents, you subtract, right? So negative 3 minus negative 3 would be 0. So you're right, Sarah. I hit something wrong. Thank you. You were right. Okay, 1.44. Yeah, that's in the middle, right? Okay, here, let's see what we get. Oh, thank the Lord. Same thing, right? Yay, thank you, Zunda. Okay, so 1.44 raised to what power equals 1.44? Okay, so N equals 1. So that means we come back to the rate law here and replace N. 1 is understood. We never write 1. You can if you want to. It would not be counted wrong. It's just not the convention. Okay? So this is the rate law. Okay, now we need rate constant, right? How are we going to get rate constant? Okay. All right. So could we just take experiment 3? We already have it written down, and we know that N is 1. You know, so how would we solve that? That would be, we would write that as K equals 3.26 times 10 to the minus third moles per liter second, and divide that by 0.275. Whoops. Confuse anybody. Moles per liter. Does everybody see what we're doing? Okay. I'm gonna come over here and check the units real quick. Moles per liter second times liter over mole, right? Because you would invert that when you multiply. Okay. Do you see what I see? Not seconds. 1 over second, which can be written as, that's how you're going to see it on the AP problems, second to the negative first power. Okay? Okay, so let's punch this in the calculator and get a number to go with that unit. Did you guys get 0.0119? Punch it in again.
Or look at the 6, that's what
Let's try another one. Let's at least get it started. 25. The rate of the reaction between hemoglobin and carbon monoxide, so here's a medical problem for us, for you folks going into the medical field. Good old biochemistry in your future. Was studied at 20 degrees Celsius. The following data were collected with all concentration units in, hey, what's that Greek letter? Looks like a U with a tail on it. Micromoles per liter. So we have concentration in micromoles per liter. Micro is a million, 10 to the negative 6. We can go back and look. If you get stuck by yourselves and you're like, gee, what is that unit? Just Google you an SI prefix chart and you can find it.
But it is the Greek letter mu, right?
Yes.
Okay.
Yes, I'm sorry. Yes, it is the Greek letter mu. In physics, it means something different. I hate that science does that. I really do. And I really hate that you got little k, rate constant, in kinetics, and then you got capital K, equilibrium constant, in equilibrium.
There's only so many letters, though.
That's true. That's true. Okay. A hemoglobin concentration of 2.21 micromoles per liter is equal to 2.21 times 10 to the negative 6 moles per liter. break time. Do you want the next hour recorded or not? Does it matter?
Are we still going over the line?
We're still going over lab and we're going to get started on integrated rate law.